Hello everyone, I am Jinghan, and today I'll be presenting our work, Banner, an image sensor reconfiguration framework for seamless resolution-based trade-offs. This is a joint work with Alexander Shearer, Saranya Rajagopalan, and Robert Lee Kanwan. To understand why we need seamless resolution reconfiguration framework, we begin with talking about continuous mobile vision applications. In recent years, more and more powerful devices have enabled a variety of continuous mobile vision applications with rich experience and broad content. For example, face recognition can continuously detect faces and add special effects on top, and fine-grained localization can continuously remind you the direction and guide you to a destination. An augmented reality application provides a unique interactive experience between the real world and the virtual objects. However, all of these interesting applications running on the mobile devices suffer from the limited battery life. Image data sensing, moving, and processing are so expensive that they will drain the battery very fast. And what can we do about it? It is well known that mobile vision systems would benefit from the resolution-based trade-offs. At high resolution, the task has high accuracy but with low energy efficiency. At low resolution, the task has low accuracy but high energy efficiency. Image resolution creates an interesting trade-off that the system should use high resolution when the task calls for it, otherwise use low resolution for energy efficiency purpose. We verify this trade-off by studying around a marker-based post-estimation application. Marker-based post-estimation forms the foundation for many AR frameworks, including Vuforia, AR Core, and AR Kit for image-based environmental understanding and motion tracking. So our case study shows that based on the distance between the camera and the marker, the task requires different resolutions to ensure a reasonable accuracy. If the camera is really close to the marker, and if we can reconfigure the sensor from 960p to 480p, the task accuracy can be maintained with a 70% less energy consumption. So we too advocate that mobile vision systems should be able to benefit from the ability to situationally sacrifice the image resolution to save energy when imaging detail is unnecessary. This sounds great. However, resolution reconfiguration incurs latency penalty. As you can see in this Linux V4L2 and Jetson TX2 board setup, the frame delivery is paused during reconfiguration and the screen cuts to black. And even worse, this problem can be identified in Android platform and also iOS. You can notice the visible gap in all those three systems. So it is because of this reconfiguration latency penalty. The resolution-based trade-off is underutilized in continuous mobile vision applications. Commercial AR applications constantly work at a specific resolution. They do not change resolution at all. And people try to utilize this resolution-based trade-off by downsampling, for which they resize the image to desired resolution. However, we see downsampling is not the cure, because downsampling actually has worse accuracy compared with working at real 480p and more energy consumption. So in this paper, we target resolution reconfiguration latency as the chief impediment for energy-efficient visual systems. And we define end-to-end reconfiguration latency and frame-to-frame latency to describe the resolution reconfiguration latency. End-to-end reconfiguration latency is the time between an application's request to change resolution and the time the application receives a frame of that new resolution. And frame-to-frame resolution latency is the interval between two frames being provided to the application in which the latter one is at the new resolution. We define two latencies because they are fundamentally different, especially in the Android OS. In Android reconfigures the sensor only after the frames stored in the pipeline for previous resolution processed. However, they're the same in V4L2 because V4L2 directly abandons those frames and immediately processes the resolution request. So we think Android performs the right operations here. So to get the design of our framework, we declare the first insight here. Our framework should be able to preserve the pipeline of existing frames while reconfiguring the sensor to another resolution. Now we understand the definition of reconfiguration latency. We wondered, where does it come from? Does it come from the hardware or does it come from the operating system? We say hardware is not the culprit. Actually, hardware register values are effective by the next frame. As you can see in this sensor datasheet, the sensor supports consecutive captures at different resolutions. However, together with the system, it incurs latency penalty. So our framework should be able to change resolution immediately, effective in the next capture. Again, hardware supports seamless reconfiguration. The reconfiguration latency penalty must come from the operating system. In the operating system, resolution reconfiguration undergoes a sequential procedure inside the media framework, which requires the application to invoke several expensive system calls. And the application invokes those system calls to interact with different kernel modules, including camera host driver, video buffer driver, and the image sensor driver. And to begin this procedure, the application sends a new resolution request, and then it calls a system call to turn off current streams. Then it calls another system call to free buffers. After that, it calls another system call to set sensor output format. After that, it calls 2 more system calls to allocate new sets of buffers. And finally, it calls the last system call to start the new streams again. And if the application requests another resolution, the whole procedure with all those expensive system calls are to be repeated. In this sequential procedure, we can see that the buffer or the memory is requested based on format. If format or controls that changes the buffer layout are to be modified, the media framework requires the streams to be stopped, which leads to this repeated memory allocation and this sequential reconfiguration. So our framework should be able to minimize format synchronizations across the video system stack while ensuring correct sensory data. So with those 3 insights, first, our framework should be able to preserve the pipeline of existing frames. And then our framework should be able to change resolution immediately, effective in the next capture. And our framework should be able to minimize format synchronizations across the video system stack. With those 3 insights in mind, we introduced Banner. Banner is a system solution for providing rapid and seamless resolution reconfiguration for continuous mobile vision applications. Those applications can now reconfigure the sensor resolution through only one system call. Banner employs 2 key techniques: parallel reconfiguration and format-oblivious memory management. Through these 2 techniques, most of the sequential reconfiguration procedures are avoided, and you can see the huge difference between the reconfiguration in the legacy system and reconfiguration in Banner. Parallel reconfiguration aims at reconfiguring the sensor while the application is processing frames for the previous resolution, such that the pipeline of existing frames is preserved and the next capture is at the new resolution. For a typical frame rate, for example, at 30 FPS, we find that the application, which is the user thread, and the camera, which is the capture thread, are not always busy. There is an interval for our reconfiguration thread to reconfigure the sensor such that the reconfiguration latency can be hidden. And we define the reconfiguration timing budget to be a function of the frame interval and the capture time. And the frame interval and the capture time are influenced by different camera parameters. However, if this reconfiguration latency falls into this timing budget, it can be completely hidden. And in all our evaluated workloads, the reconfiguration latency can always be hidden. Format-oblivious memory management aims at maintaining a single set of frame buffers to mitigate the format synchronizations across the video system stack. In detail, Banner only requests buffer once for the highest supported resolution, and then it delivers the frames based on how many bytes are used. Through this, consecutive buffers may contain frames at the different resolutions, and we observe that only the application and the sensor are required to know the resolution to ensure correct sensory data. So again, through parallel reconfiguration and format-oblivious memory management with Banner, most of the procedures are avoided, including repeated start and stop streaming and this repeated memory allocation. And set sensor format in Banner is in parallel with the process images such that the next capture is at the new resolution. So Banner realizes seamless reconfiguration compared with the legacy system. And during resolution reconfiguration, there's no gap at all. And we evaluate Banner on a Jetson TX2 board with an onsemi AR0330 sensor. We run 3 workloads. The first one is a display-only workload. It gives us some preliminary results. And a cloud-based offloading workload demonstrates Banner's utility in cloud computing. And a marker-based post-estimation application, which is the same application we studied in our case study. We measure the end-to-end reconfiguration latency and the frame-to-frame latency by retrieving the system stems at the application level. And we measure the system power consumptions for different components on board, including SoC, DDR, CPU, and GPU, by retrieving the sys files. The results show that Banner can halve the end-to-end reconfiguration latency in this offloading at 30 FPS workload. And frame-to-frame latency in Banner is equal to the inverse of the processing frame rate. Comparing to 5 frames drop, 6 frame drop, and 3 frames drop in each workload, Banner reconfigured the sensor with 0 frame drop. Now we understand that resolution reconfiguration latency is reduced, but how much energy can be saved with Banner? In the display-only workload, comparing with downsampling from 1080p to 480p, all components on board working at real 480p consumes less power, which in total consumes 43% less power. In the cloud-based offloading workload, all components on board also consumes less power working at real 480p, which in total consumes 49% less power. And in the marker-based post-estimation workload, this trend continues with a 16% total energy, power saving. So we observed that reconfiguring the sensor is more energy efficient than downsampling. It's the reconfiguration latency penalty. As a result, Banner unlocks the resolution-based trade-off for energy-efficient continuous and now balance the accuracy and energy trade-off on the fly. However, there are several limitations in Banner. First, Banner allocates more memory than it is needed for the smaller resolution. However, this is acceptable as memory is cheaper and cheaper. And also the additional memory allocation didn't incur power overhead because the memory power depends on the data rate. Second, if frame rate is low, end-to-end reconfiguration latency reduction can be less effective because Banner preserves the pipeline of the existing frames. However, Banner still reconfigured the sensor maximize energy savings for a variety of vision applications. Second, we will explore the architectural influence for integrating Banner to machine learning applications. And third, we will try to integrate Banner to more operating systems to benefit more users. So in summary, continuous mobile vision applications can benefit from the resolution-based trade-offs to extend the battery life. However, resolution reconfiguration in current systems incurs latency penalty because of the reconfiguration procedure, a sequential reconfiguration procedure. And we introduced Banner Media Framework through parallel reconfiguration and format oblivious memory management. Most of the reconfiguration procedures are avoided. And the applications can now reconfigure the sensor resolution through only one system call. Banner completely eliminates the frame-to-frame latency, which means 0 frame drop during resolution change, and it enables a substantial saving for a variety of workloads. And we believe that Banner will enable a future of energy-efficient visual systems. Thank you, and I will be happy to take any questions.